those two booths. All right, that's really all I'm going to say on my own. I thought it would be very, very interesting to invite Andy Bechtolsheim from Arista Networks to join me this morning as part of this announcement. Andy's been a very close partner on the development effort, and I think he has quite a lot to say about the role that silicon photonics can play in the future of disaggregated server architecture. So let's welcome Andy Bechtolsheim.
Hey, good to see you.
Good to see you. So Andy and I'm going to embarrass you. Andy and I go way back. We've known each other for more than 35 years. I first met him when he was a student at CMU. I tried to hire him, but then I moved to Oregon. Andy wanted to stay in the Valley, and we sort of separated at that point, and have only recently gotten back together to focus on this the silicon photonics technology. So it's very exciting for me to have Andy here today, and we're going to take a seat over here, and and chat away. And Andy, why don't I give you the first question, and then we'll toss it back and forth.
The first question is?
That's the first question.
Are you supposed to ask me this question? I'm sorry.
No.
So people have talked about disaggregation for, I don't know, the last 30 years.
Right.
But what's different now? What does this technology mean to disaggregation?
Well, I think disaggregation is one of those things that people talk about. People imagine, but I think it's proved in practice to be much more difficult to achieve. And I've kind of watched, as I said, as a student of rack architecture, I watched these, the blades and the rack servers get more and more stuff sort of packed into them. I think when we were using that approach to build high-performance computers, we were already thinking of disaggregation, but it's expensive, and I think it's really been perhaps limited to very high-end systems. Now, I know Arista's working in this space, so what's your view?
The practical problem is that the faster the link goes, the less long they go in copper. So at 25 gigabit per second link, it's tough to get it working, on a board, never mind a rack. And what has been missing, quite honestly, is a technology that allows this speed of link to get out of the box and connect to other boxes. And if you look at the currently available optics for 100 gigabit, they're so expensive, they clearly don't solve the problem. So it comes down to three things, which is the speed, the power consumption, which drives density, and the cost. And the Intel Photonics technology is really the first one we have seen that has all the right three attributes to actually enable taking the PCI out of the box and allowing Ethernet or InfiniBand or other things to go over that. So it's really a universal transport layer, in my mind, as important as PCI Express, except it's not in the box, but it's the thing that goes out of the box.
Right, right. Well, it's been a how should I say, a decade-long effort to create the photonic technology, but I agree with you. I think once you can achieve that right combination, of speed and power and cost, the potential here is enormous.
I should mention, people have tried this with copper cables. I'm not sure you've seen these pictures, but if you have a rack full of thick PCI copper cables, there's so much bulk to the cables that it almost blocks the airflow going through the system.
Right.
So that's not practical either.
Yeah, and that's another thing I think. Yeah, that disaggregation buys, because now you can sort of optimize airflow on a sort of module by module basis. When if you're trying to get around heat sinks and disk drives and power supplies, the airflows get very complicated.
But even with copper cables, maximum reach is like 3 to 5 meters, which means there's still no solution today that's available that's low cost, 100 gigabit, goes across the data center.
Right.
So we are very excited about this.
Okay. You've had the opportunity to I guess, get your hands on the first of these, of these modules, these 100 gigabit per second modules, what's your initial impression?
Yeah, so we're looking at this in the context of for future 100 gigabit Ethernet switches. We're not making any product announcements today, but what I can say is, the modules do work. We're playing with them in the lab. And the whole thing about 100 gigabit Ethernet is it's not practical until the cost of the optics comes down. So the current optics are so expensive, I don't even know how to put it. They basically inhibit the market. Whereas with this kind of technology, 100 gigabit becomes a very viable technology for the networking industry, and it will take off, as soon as this is shipping.
Well, I think we're there. Or we're very close. And in fact, what we've been doing the last couple of years is taking all of what we've learned in research and basically taking it into the factory and proving that we could build the technology in high volume, get good yields, be highly testable. It always kind of blows my mind to think that we've been at it for a decade. But
yeah, in fact, let me mention one thing. I'm not sure people realize how optics are being built today, but basically there's huge factories in Malaysia and Thailand and in China, I'm sure, where there's a lot of people, with microscopes and usually ladies that have very calm hands aligning the fiber with the laser so the light couples in and out. And it's basically a manual intensive, low yield, or just a very manual assembly. You wouldn't believe it if you see the final product, but basically people do this by hand. And the much better way to build this is as a silicon process and stamp it out at the wafer level, which is what Intel is very good at.
Well, when we started, when we would even juxtapose those two words, silicon and photonics, people would start to laugh because everybody thinks, well, silicon's not an optical material. You can't, the first thing is, well, you can't build a laser. And by the way, you can't build much else. And I would say, if you go back early in the last decade, when we were sort of, down with modulators or detectors that were maybe a gigabit per second in silicon, we thought maybe they might actually be right. But, but the research, took us to the point where we had integrated lasers with our hybrid silicon laser. We had, we had modulators, we had detectors, we had muxes and demuxes, and we had, the drive electronics and the, and the transimpedance amplifiers and all of that to build a complete subsystem.
So is it a secret how long you have been working on this?
No, it's not. Actually, and I would encourage you who now want to go back and look at the history, to look at the publication record. If we can get that slide up, I think they had. You can see, there's many publications, in Nature and in Science and in Scientific American and Photonics, Laser World, MIT Technology Review. They've talked about these advances for some time. What we haven't talked about, and I think some people noted that we went quiet over the last couple of years. I think almost 3 years ago, we showed a 50 gigabit per second module. People thought, well, maybe we had given up or thrown in the towel. What we were doing was we were in the factory and out on the floor developing the manufacturing technology, the process technology, to create, as Andy just described, a fully monolithic photonic subsystem. So we build these things just like you build any other kind of integrated circuit. It's built in a standard chip factory. I think one of the most interesting things, and it's highlighted here if you look at the photos in the upper right, is we also figured out how to test them like you test integrated circuits. So these hand-built optical modules that Andy just spoke to, you can't test them until they're completely built. We don't have to slice them up and package them and all of that and then test them. We can actually test them while they're still at the wafer level, and I mean both electrically and optically. So when you see the optical part of the test running, I have to tell you, it's a bit eerie because the probe never contacts the wafer because it's actually reading the photonic signals at the appropriate test points on the die. So when we complete that test, we know which die are good and which die are bad on the wafer, which can only help further reduce our costs and ultimately reduce prices over the long term. We've also built, I think, quite a formidable patent library around the technology. So, I think it's going to give Intel the ability to, build this business over the coming year.
Yeah. So this is really a remarkable breakthrough in terms of manufacturing technology, testing technology to build high volume, low cost, low power, 100 gigabit photonics.
Absolutely, absolutely, and we see, the sort of the inherent scalability of the technology. We're not, and this I think is apparent if you read the research. We're not even close to the single, the single lambda speeds, the single color speeds that we've described in the literature. So we can make those photons go faster. We can put more stuff on the fiber. We can add fiber. So we're scalable in 3 or 4 dimensions. So we think it's going to be a very powerful and versatile technology.
So to sum this up from my perspective, I think everybody believes that Intel is like clockwork on Moore's law, with a new CPU chip coming out every 18 months or thereabouts. And there was actually a risk that if the interconnect technology doesn't keep up with Moore's law, that the interconnect would become the limiting factor in these much larger cloud distributed, disintegrated computing installations. And this is the kind of technology that will literally change the tide here by allowing a very high bandwidth interconnect, not just within the rack, but across a whole bunch of racks in a data center.
And I think it has to be said that I think it'll unleash all kinds of new software development.
Yeah, at the distributed application basis,
yeah,
because
the application
you no longer have to worry about data placement or this data's over here, but we can't get over there kind of thing.
Right, and so ultimately, I do believe the ultimate end user, the ultimate customer will see the benefit of it. It won't just be this abstract thing because we'll be able to do things in the data center that we just haven't been able to do before.
So somebody could build a data center with 100,000 servers that are connected with 100 gigabit non-blocking bandwidth. Do we know such a company?
Sounds like a good idea to me.
Okay, sounds like a good idea.
Okay. Anyway, I want to thank Andy for joining me on stage today and and sharing his views and his early experience with the Intel Photonics technology. And Frank is here, so.
Great. Thank you.
Thanks very much.
Thank you.
Thank you, Justin.
Thanks,